rows, AI and AJ, different rows. Then if I swap, get of the determinant. Okay, so basically, matrix I IJ order is the determinant of AJ AI order. Everything else same. Okay, basically, swap two rows. You get a negative sign for the determinant. All right. Then the second thing is that determinant is linear on row of this matrix. Okay, so basically linear. If I replace AI by 2AI, I get twice the determinant. All right. If I replace AI by AI plus I, then I get the determinant of the matrix I, everything else being the same, plus the determinant with BI here, everything else being the same. Okay. Thirdly, this is called the normalization constant. So it says that determinant of the identity matrix. Okay. The last property is simple and easy, right? So now why this is called elementary properties? I think if you look back a little bit to elementary matrices, you will see what this is. So basically, this is the compute the determinant on elementary matrices. We have three kinds of elementary matrices, right? So one, of course, is this one, right? 1, 0, 0, 3. Okay, the second one pops. Okay, 0, 1, 1, 0. Right? And then the last one, add a row to another. So 1, 3, 0. Okay, you look at the three properties, what the determinant value of these three matrices are. So for example, property tells us that if we swap two rows, the determinant of the element is -1. Okay, then the second one tells us that if we add it to another, what the determinant is. The last one plus the second one, determinant identity is 1, tells us that this guy, 1, 0, 0, C, the first guy scaling one row, the determinant is C. Okay, then with this that, we know what the determinant is for square elementary properties. The reason is by doing the REF process, you can factor any matrix in your product elementary matrices, right? And then you just multiply all the determinant values together. Okay, so this is why these are the instances. Then I think there are some not important properties as corollary. Okay, 4, 5, and 6. These are all covered in worksheet 21. So firstly, determinant of AB equals of A times determinant of B. Okay, so determinant of A inverse equals determinant of A inverse. Or I guess you have a question if determinant is A. So actually, there is another reflection of this property. So determinant A does not equal if and only if A is invertible. Okay, so last property we want to mention is that if A is similar, that equal inverse BA. Sorry, S inverse BS. Okay, then determine A equal. I will leave this as an exercise. It easily follows from property 4 and 5. On the worksheet 21. All right. Then we are going to talk about the most complicated stuff, which is the computational definition. So let's look at directly the 3 by 3 because we already know the 2 by 2. Our example is a 3 by 3 matrix. Given the fact that we are the function 2 matrix determinant, we are going to talk about and sign in this case. Okay, so what is a pattern is a product of elements in the matrix. Okay, so basically have A1, J1, J2, J2, Jn. J1, J2, Jn is a reordering of 1 through n. Okay, so now let's look at the examples. So we have A1, A2 to A3, 3, right? This is our natural choice. In this example, A11, A2 to A3, 3. So because J1, J2, Jn is a reordering, okay, how many different ways do we have to reorder numbers? 1, 2, 3, 6. Right? So we take 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1, and 3, 1, 2. So totally there are. Okay, so we have 6 reordering of 1 to 6 parts. Okay, the next thing we have to do is the sign. Okay, how do we assign a plus or minus to these patterns? Basically, we have a concept called inversion. So J2 through reordered. Okay, A3. Okay, then we look at the pairwise 1, 2. Basically, there's no inversion for this pattern, and the sign is -1 to the power of 0. Okay, so basically the law is going to be -1 to the power of the number of inverse. And the next 1, 3, 2. You look at 1, 3, then no inversion, right? If you look at the 3, 2, that's inversion. Then it's inversion. So basically, there's 1 which means the sign is -1 to the 1, which is -1. Okay. I'll let you guys do the following computations. But anyway, answer of signs are listed here. And then in total, we compute the detail of a 3 by 3 matrix. We just write down all the 6 terms and then multiply their correct. We are done. Determinant. So basically, that's a computational information. So how many inversions are there in an n by n matrix? The answer is n factorial, right? Okay, what is the sign of each pattern? That's going to be complicated, right? So that's where you guys be able to compute the 2 by 2 and 3 by 3 matrix. Okay, so then with the computation given, we look back to the properties. So this is a very surprising fact. If you look at the property, which think that elementary properties, which think that determinant satisfies the row versus foundation, right? Each rows, and determinant identity is 1. So if we satisfy all the properties, which is the real, then it has to be the determinant function with the unit. Okay, so I think I will stop here for the introduction of the lecture. Hope this is helpful. At least this covers all the material you need for the exam and for